Hi everyone. In today's video, we're going to take a look at the absolute value function. We'll start by taking a look at the definition of the function, and then we'll take a look at a couple of inequalities that involve absolute values that are extremely important in the study of calculus. So let's start with the definition of the absolute value function. So the absolute value is defined as follows. The absolute value of a being a number, is represented by a surrounded by two vertical parallel lines, and this function is equal to a if a is greater than or equal to 0, or minus a if a is less than or equal to 0. So what this means is that the absolute value of a number is always going to be positive. So for example, if a is equal to minus 3, then the absolute value of a is equal to minus 3, right? Because we invoke this second part here because a is negative, which means that the absolute value of a is equal to the negative of the number, which is the negative of negative 3, and that's 3. On the other hand, if a is equal to, say, 4, then the absolute value of a is simply equal to 4, right? Because a is already greater than 0, which means we're here, which means that the absolute value of a is simply equal to a itself. Okay, so as you can see, regardless of whether we have a negative or a positive number, the absolute value will always be positive. And it's very useful to think of the absolute value of a number as the actual magnitude of that number, by which I mean how far that number actually is from 0. So for example, if I were to draw a number line, I'll put my 0 here. If a is equal to minus 3, then it's over here somewhere, to the left of the number line. But the distance between a and 0 is 3, right? It's 3 units away. And that 3 is obtained by taking the absolute value of the number, the absolute value of minus 3. Similarly, if a happens to be positive, say, for example, a is equal to 4, then the absolute value of a is going to be equal to this distance from 0 to 4, right? This is going to be 4, which is equal to the absolute value of 4. This is equal to the absolute value of minus 3. So you see, the absolute value of a number is really a measure of its magnitude in the sense that it's a measure of how far the number is from 0. Another way to look at the absolute value is to kind of take this definition and sort of flip it over. So we can say, for example, that a is equal to minus its absolute value if a is less than or equal to 0, or a is equal to its absolute value if a is greater than or equal to 0. All right, so once again, if a is equal to minus 4, then the absolute value of a is equal to 4, and therefore the negative of the absolute value of a is equal to minus 4, which is in fact equal to a. So that proves that's an example of this first case. The second case here is a is equal to 4, then the absolute value of a is equal to 4, which is in fact equal to a. So once again, we see that we can write these two statements and they're perfectly correct based on the definition of the absolute value function. All right, now another way to think about the absolute value function is that you can get the absolute value of a number a by taking the square root of a squared, where we understand here that the square root function is really referring to the positive square root. Okay, and this is a typical convention in mathematical textbooks. So whenever we talk about a square root, we're going to talk about strictly the positive square root. Now we know that a squared actually has two roots, right? It has a and minus a. You can square either one of those, you're going to get a squared. But again, we're going to work on the assumption that the square root of a number is always going to refer to the positive square root. Finally, the last way to think about or to get the absolute value of a number a is to realize that the absolute value of a is equal to the maximum of either minus a or a. Let's take a quick example. If a is equal to minus 4, then minus a is equal to 4. And then if we take the maximum of minus a, which is 4, and plus a, or just a, which is minus 4, well, obviously the maximum is this one here, which is going to be equal to 4, which is indeed equal to the absolute value of A, which is the absolute value of minus 4. Okay, so you can see how this, and this, the original definition that we started with, are, for all practical purposes, equivalent expressions of the absolute value function. Okay, let's move on now and take a look at a couple of inequalities that appear in calculus very often because it's important in the study of limits, which are basically the basis for all of calculus. So we're going to start with an inequality that looks like this one. The absolute value of some variable x is less than or equal to some number d. We're going to consider that d is a constant, and we're going to restrict ourselves to the condition where d is greater than or equal to 0. Now, why would we do that? Well, let's take a look at what happens when d is less than 0. So if d is less than 0, then this original inequality is x less than or equal to d, but d then is less than 0. So kind of following through, you can see then that x, absolute value, is less than 0. Well, the absolute value of any number is always going to be positive, which means it will never be less than 0 because it will never be negative, which means that there are no possible values of x that would satisfy this original inequality up here if d is less than 0. Okay, so we're only going to consider situations where d is greater than or equal to 0, because if d is less than 0, there are no values of x where we can solve for this thing, so it's of limited interest. Okay, so no possible values of x. All right, so let's start again with this inequality, x less than or equal to d, where d is greater than or equal to 0. And to understand what this inequality actually means, what possible values of x can take on in order to satisfy this inequality, we're going to consider two situations. In the first situation, we'll assume that x is greater than or equal to 0, in which case the absolute value of x is actually equal to x itself, right? Since x is positive, the absolute value of x is simply going to be x itself. So I can therefore rewrite this inequality, absolute value of x less than or equal to d, I can rewrite it simply as x less than or equal to d. My original assumption was that x was positive, so x is greater than or equal to 0. And combining these two, you see that x is less than or equal to d, but greater than or equal to 0. So if I were to sort of draw out on the number line the possible values of x in this case, I would draw the 0 here, the d here, and x is between 0 and d, which means these are all the possible values that x could take on to satisfy the inequality, assuming x is positive. Now, what happens if x happens to be negative? In this case, the absolute value of x is going to be equal to minus x, right? Because the absolute value of x is positive. In order to get a positive value from a negative number, I have to take the negative of it. So in this case, the absolute value of x is equal to minus x, which means that this inequality, x less than or equal to b, can be rewritten minus x less than or equal to d, right? And again, d is positive in this case. I can put the d on the left, the x on the right, and that then becomes minus d less than or equal to x, but I prefer to have the x on the left, so I'll just rewrite this as x greater than or equal to minus d. Now, an easier way to get from this to this is as follows. I'll start with minus x less than or equal to d. I'm going to multiply through the entire equation by minus 1. So minus x multiplied by minus 1 becomes plus x. D multiplied by minus 1 becomes minus d. Then I'm going to flip the side of this inequality. So instead of being less than or equal to, I'm going to say greater than or equal to. And there we go. These two statements are in fact identical. Okay, the same thing, the same result I got here, except in a slightly quicker way and an easier way to do without making errors. So going back to what we have up here, we have x is greater than or equal to minus d. We also have that x is less than or equal to 0, which means that x is less than or equal to 0, but greater than or equal to minus d. Okay, so this one's here, this one's there. And what this means, again, if I take a look at the number line, is that x is between 0 and minus d. So we can take on any values between minus d and 0, and this inequality will hold. Again, the assumption in this case was that x was negative or 0. Now I can combine these two intervals, right? Because then I will be covering every possible value of x that would satisfy the inequality. So the first interval was between 0 and d. The second one was from minus d to 0. Combining the two, they just kind of are contiguous. They just come together nicely. And I can see that, in fact, the total solution for this inequality is that x is less than or equal to d, but greater than or equal to minus d. Another way of writing this is to realize that x has to be less than or equal to d, and x has to be greater than or equal to minus d. Both conditions must be true, right? What would happen if x was only less than or equal to d? Well, if x is only less than or equal to d, then really I could take on any values, including values that are way past minus d on the negative side of the number line. And that's obviously not the case, right? I have to stop here. And that's where the second condition comes in, right? So both of these conditions must hold true for the inequality x less than or equal to d, d greater than or equal to 0, to actually find possible values of x that satisfy this inequality. Okay, so we have this nice little interval that goes from minus d to plus d. So really, when I say x is less than or equal to d, I'm really saying that the distance between 0 and x cannot exceed d, cannot be greater than d, right? So x is somewhere in this interval, which is no more than d units away from 0. All right, let's continue our discussion now by looking at a different inequality, where instead of saying that x is less than or equal to d, we're going to say that the absolute value of x is greater than or equal to d. Once again, though, we're going to assume that d is greater than or equal to 0. Why? Well, let's take, as we did before, let's look at the situation where d is less than 0. So the absolute value of x is greater than or equal to d, and d in turn is less than 0, which means that x would have to be greater than or equal to a negative number. Okay? But the absolute value of x is positive. It's always positive. It's always positive or 0, actually, which means that it will always be greater than or equal to any negative number, which means that x can take on any value whatsoever. This equality will always hold true if d is less than 0. So that kind of limits the value of considering situations where d is less than 0. So we're going to restrict ourselves to situations where d is positive or 0. Okay, again, it's kind of the flip side of what we saw with, remember, with x less than or equal to d. D less than 0 means no possible values of x. On the other hand, if x is greater than or equal to d, where d is less than 0, all x satisfy the inequality. So in both cases, it's not especially useful to consider situations where d is less than 0. Okay, so having looked at that aside, let's take a look now and consider this inequality. X absolute value is greater than or equal to d, d greater than or equal to 0. And once again, we're going to consider, we're going to look at this thing in sort of two pieces. We're going to start by saying, okay, what happens if x is greater than or equal to 0? Then the absolute value of x is equal to x, which means this inequality can be written x greater than or equal to d. We also have x greater than or equal to 0, which means on the number line, d is here, and those are the possible values of x. The x greater than or equal to 0 is kind of subsumed or included in the condition that d is greater than or equal to 0, so it's not really going to be of any great importance to us in this case. Now, on the other hand, if x is less than or equal to 0, then the absolute value of x is equal to minus x, in which case this inequality becomes minus x greater than or equal to d. Multiplying through by minus 1, we get x and minus d. Flip the side of the inequality, and we get x less than or equal to minus d. And then we also have x less than or equal to 0. That was our initial assumption. And so if I put this again on the number line, here's 0, here's minus d. X has to be less than or equal to minus d, which means it's to the left of minus d. Combining these two intervals together, what I see is that x can take on any values which are greater than d or less than minus d. Notice how I said or. In the previous case, where we considered the inequality absolute value of x less than or equal to c, we ended up with this interval. In this case, we end up with the kind of the opposite of this interval, is everything but that interval. Okay, so x greater than or equal to d really means x greater than or equal to d, or x less than or equal to minus d. And that's in contrast to x less than or equal to d, having the solution x is less than or equal to d and x greater than or equal to minus d. Okay, so two very different situations. One where the interval is continuous and is contained between minus d and plus d, and one where the interval is discontinuous. All right, so it's basically got wings, and you're either to the right, where x is greater than or equal to d, or on the left, where x is less than or equal to minus d, but you cannot be both. Okay, let's take a look now at a couple of somewhat more complicated inequalities involving absolute values. And we're going to consider the inequality x minus c less than or equal to d, with d greater than or equal to 0. So similar to what we did before, except that we've introduced another constant, namely c, and we're going to see what that does to the interval of possible values for x. We're going to stick with the same assumption, though, that d is greater than or equal to 0, because otherwise we're going to end up with the same situation we did before, namely that there are no possible values of x that satisfy this inequality, and therefore the inequality is of kind of limited interest. Let's go through the argument. Let's assume that d is less than 0. That would mean that x minus c is less than or equal to d, which is in turn less than 0, which means that x minus c, absolute value, is less than 0, which is not possible, because the absolute value of x minus c will always be positive. It can never be less than 0, which means there are no possible values of x that satisfy this inequality. All right, having laid that little problem to rest, let's now take a look at this inequality and find out what values of x will actually satisfy it. So, as we did before, we're going to start with the assumption that whatever's in the absolute value is actually positive, or 0, greater than or equal to 0. In this case, the absolute value of x minus c is going to be just equal to x minus c itself. And then this original inequality can be written x minus c less than or equal to d, or x less than or equal to c plus d. Just take the c, move it over to the right, and change the sign. The original inequality is x minus c greater than or equal to 0, which is x is greater than or equal to c. Putting these two together, we see that x is greater than or equal to c, but less than or equal to c plus d. So on a number line, where c is here, c plus d would be here because d is positive, and therefore c plus d will be to the right. These are the possible values of x, assuming x minus c is positive or 0. On the other hand, if we assume that x minus c is less than or equal to 0, in other words, negative or 0, then the absolute value of x minus c will be equal to the negative of x minus c. Very important to remember the brackets here. And if I multiply through my minus 1, this is simply equal to minus x plus c. Okay, so this inequality then with the absolute values can be written minus x plus c less than or equal to d, and then minus x less than or equal to minus c plus d. Multiplying through everything by minus 1, I end up with x, c, and minus d. Flip the direction of the inequality, it'll become greater than or equal to, and I end up with x greater than or equal to c minus d. The original condition here is x minus c less than or equal to 0, which means x less than or equal to c. So these two together give me x less than or equal to c, but greater than or equal to c minus d. which, if I put this on a number line where C is here, C minus D is here, again, D is positive, therefore C minus D will be to the left of C. These are the possible values for x, assuming x minus C is negative or 0. You'll notice that I made no assumption whatsoever on the actual sign of C. It doesn't matter, okay? Nothing in the argument I've given depends on the actual sign of C. It's of no consequence. It's the x minus C that is of consequence. Combining these two intervals together, here's C plus D, here's C minus D. This was the first interval, this was the second interval. So putting them together, we can see that all possible values of x that satisfy the inequality have to be less than C plus D and greater than C minus D. Again, this is an and condition. Both of these conditions must be true. And then you'll find a valid value of x that will satisfy the inequality. Okay. Now you'll see that this looks kind of very similar in terms of the solution to x less than or equal to D. In this case, we had an interval which was centered around 0, okay, and was 2D wide. In this case, we have an interval which is centered around C, which is 2D wide, right? It ranges from minus D to plus D around C, which means the width of it is 2D wide. This is D and this is D, right? So the width is 2D. And really, if you think about it, this is really the same thing as x minus 0 is less than or equal to D. So it's the same inequality as x minus C less than or equal to D, where C is simply equal to 0. Okay, so this one here is a generalization of this one here. Okay? Now, of course, we can do the same kind of thing as we did before and take a look at what happens when we consider that, or when we look at the inequality x minus C greater than or equal to D. Once again, we're going to assume that D is greater than or equal to 0. Why? If D is less than 0, then x minus C is greater than or equal to D, which is in turn less than 0, which means that this has to be greater than or equal to a negative number. Once again, since the absolute value of anything, including x minus C, must be positive, then any possible value of x will satisfy this inequality, which means it's a sort of limit of interest because any value of x will satisfy it. So, having laid that to rest, let's move on. And we'll do the same kind of argument we did before. Let's assume first that x minus C is greater than or equal to 0. Then, in this case, then we have that x minus C is equal to x minus C. So the absolute value of x minus C is simply equal to x minus C. And this inequality can be written x minus C greater than or equal to D, or x greater than or equal to C plus D. We also have this one here, the original assumption, x minus C greater than or equal to 0, which means x greater than or equal to C. So if I were to draw this thing on a number line, I would see that here's C plus D, and x has to be greater than C plus D. So it's going to be automatically greater than C anyway, greater than or equal to C. So this kind of secondary condition is not all that interesting in this case. Now, if we then make the assumption that x minus C is less than or equal to 0, then the absolute value of x minus C is minus x minus C, which is minus x plus C. And in this case, then this absolute value inequality can be written minus x plus C greater than or equal to D, which means minus x greater than or equal to minus C plus D. Multiply through by minus 1, you have x, C, and minus D, and flip the direction of this inequality from greater than or equal to less than or equal to, and we have x less than or equal to C minus D. The original assumption was that x minus C is less than or equal to 0, which means that x is less than or equal to C. And if I draw this on a number line, here's C minus D, then these are all the possible values that x can take on, right? They're less than or equal to C minus D. So this condition, x less than or equal to C, is kind of taken care of by this one automatically. Even if D is equal to 0, that condition is going to be met perfectly well. So now combining these two intervals together, we see that C is in the middle, C for center. This is C plus D, and X can take on any values greater than C plus D. And we have C minus D, and X can also take on values that are less than C minus D. In either case, the inequality will be satisfied, which means that we have the condition that X is greater than or equal to C plus D, or X is less than or equal to C minus D. So once again, it's very similar to the situation X greater than or equal to D, except that now, instead of everything kind of being centered on 0, it's being centered on C. So all we've done is we've kind of moved the intervals over such that it's centered on C instead of D. Right, so these inequalities, X less than or equal to D, X greater than or equal to D, or their generalizations, X minus C less than or equal to D, X minus C greater than or equal to D, okay, are very easy to study. In this case, where this is C plus D, this is C minus D, we're dealing with this interval. In this case, we're dealing with this intervals, or these two intervals, here and there.